Alright guys, the next thing we're going to talk about is rates of change. And we already have talked about average rates of change. It's just the slope of the secant line, which we use the normal slope of a line formula to find. Instantaneous rate of change. The last chapter we had to estimate the instantaneous rate of change. If you remember, we would try to find it at a point, and we would have to pick points that were close to it. Like if we were trying to evaluate it at 2, we would pick 2 and 2.001 and find the slope of the line that way, and that would be a good estimate. But now we have this handy dandy tool called the derivative, so we can use the derivative at that point to evaluate the instantaneous rate of change. And the graphical difference, as y'all know, the average rate of change is the slope of the secant line, whereas the instantaneous rate of change is the slope of the tangent line. So let's talk about an example real quick. We have a table over here that contains data on the temperature on the surface of Mars at Martian time t, and it was collected by NASA Pathfinder space probe. We're going to calculate the average rate of change from temperature t from 6:11 a.m. to 9:05 a.m., and we're going to use the figure down here to estimate the rate of change. So in part A, we will be using the slope of a line equation to find the secant line, and in B, we're going to be finding the slope of the tangent line. So here's our table, and we're calculating the average rate of change from 6:11 to 9:05. So we need to find excuse me, we need to find 6:11, which is right here, and we need to find 9:05, which is right here. So we're going to do change in y over change in x. Now this change in x down here, we had almost 3 hours between here, so we take the 2 hours and we add however many minutes this is divided by 60 to get 2.9 hours, and when we divide that out we get 9.4 degrees Celsius per hour. Don't ever forget to use your units on these types of examples. In part B, we have a picture of the tangent line here, and we want to try to estimate the slope of the tangent line. So we can find a point that we can easily find the values for. So they have point A here. That one looks pretty easy. So at 4:48, it's approximately negative 51. So we can use the equation that we used in the last example, y minus y1 over x minus x1, to get 3.7 degrees Celsius per hour. Alright, another example. If we let A equals pi r squared be the area of the circle of radius r, I know all of y'all knew that already, we're going to compute the derivative of the area with respect to r at when the radius equals 2 and when the radius equals 5, and then we want to sorry guys, we want to discuss why the derivative is larger at 5. Alright, so the first thing we need to do is take the derivative of the area, and we get 2 pi r, which is the circumference of a circle. That's kind of cool. And now we're going to plug in 5 and 2 into this equation to see what dA dr equals at those points. So when I plug in 2, I get approximately 12.57. And when I plug in 5, I get approximately 31.42. And if you think about it, if my radius is bigger, then my area has to be bigger. So the derivative measures how the area of the circle changes when the radius increases. So of course, when my radius is larger, the area of the circle is larger, and thus increasing more quickly. So the effect of 1 unit change. Sometimes we don't need to know the exact change, but we just want to know what happens if we add 1 or take away 1 unit of the something that's changing. So we can use the quotient, the difference quotient, like we used back a long time ago when y'all hated it. And we can let h be 1. So in doing that, we're going to let this h be 1 and this h be 1, and that will compute the effect of 1 unit change. And you'll get f prime of x equals the difference quotient evaluated 1, which is f of x sub 0, which is just your x value that you're going to use, plus 1 minus f of x sub 0. So this could be like 61, and this could be 60. So let's look at an example. For speeds s between 30 and 75 miles per hour, that should be an h, the stopping distance of an automobile after the brakes are applied is approximately this equation right here. So this is the distance it takes to stop the car. For s equal to 60 miles per hour is what we're looking at. we want to estimate the change in stopping distance of the speed is increased by 1 mile per hour. And then we want to compare our estimates to the actual increase in stopping distance. So first, we're going to find the change at 60 miles per hour, and then we'll use our equation that we just got to do 61 minus 60, and then we'll compare by actually plugging 61 into the equation. Alright, so first we have to find the derivative. When we take the derivative, we get 1.1 plus 0.1 s feet per miles per hour. And then we want to evaluate that at 60. And when we plug in 60 for s, we get 7.1 feet per miles per hour. Now we're going to use that equation we just had, where we had f of x sub 0, where x sub 0 is 60, plus 1 minus f of 60. And we get f of 61 minus f of 60, which is approximately the derivative of 60 from what we just saw in our difference quotient when it's evaluated at 1. And we get 7.1 feet. And this right here is the change in stopping distance. Thus, when you increase your speed from 60 to 61 miles per hour, your stopping distance increases by approximately 7 feet. And now we are going to compute it exactly. So the actual change in stopping distance, if f of 61 and f of 60 equals 7.5, so the estimate is fairly accurate. We went from 7.15 is the exact, and we had 7.1 back here, so it's fairly accurate. Alright, another example of using this plus 1 or minus 1. A company data suggests that the total dollar cost of a certain flight is approximately this equation right here, where x is the number of passengers. So we want to estimate the cost of adding a flight that already has 150 passengers. I'm sorry, adding a person that already has 150 passengers. And then we're going to compare our estimate with the actual cost of an additional passenger. And then we're going to try to figure out if it's more expensive to add a passenger when there's 150 on the plane, or if there's 200 on the plane. So part A, we estimate the marginal cost at x equals 50 by the derivative. So we do the derivative of our equation evaluated at 150, which is 39.75. So it costs approximately $39.75 to add one additional passenger when there's 150 people on the plane. In part B, the actual cost of adding one additional passenger is C of 151 minus C of 150. When you plug 151 into our equation, we get this number. When you plug 150 into the equation, we get this number. So it's actually $39.60. So that's fairly close. Alright, in part C, we want to decide if it's cheaper to add one when there's 200 people or 150 people on the plane. So, to find the marginal cost at x equals 200, we take the derivative evaluated at 200, and we get $28. So we see that $28 is less expensive. So it's more expensive to add people on the plane when there are 150 passengers. Alright, linear motion. This one's a big one. Linear motion is motion along a straight line, so it could be, horizontal motion along a straight highway with you driving your car or walking or riding a bike. Vertical motion of a falling object. So we're going to let s of t denote the position or distance from the origin at time t. And velocity is going to be the rate of change in position with respect to time. So velocity is the derivative of our s of t function. Alright, the sign of velocity indicates the direction of motion. So if s of t is the height above ground when velocity is positive, it indicates that the object is rising. And speed is the absolute value of velocity. So if we look at this figure right here, this is a graph of a distance versus time. Figure 6 shows that the position of a car as a function of time. So the height of the graph shows the car's distance from the origin. So from here all the way up shows the distance the car has gone. The slope of the tangent line is its velocity. So let's investigate this graph a little further. Alright, speeding up or slowing down. The tangent lines are steeper on the interval from 0 to 1. So we have steep tangent lines here. So the car was speeding up during the first hour. Then they get a little bit flatter as we go from 1 to 2. So the car slowed down a bit in the second hour. And then the graph is horizontal over 2, 3. So my tangent lines are 0, which means the driver stopped. Maybe he stopped to get a cup of coffee or, hang out a minute. And then he looks like he returned to the same spot here. So he was going and then he had to turn around. So maybe he forgot something. And then the average velocity of the whole entire graph, it looks like the graph rises more over 0, 2 than over 3, 5. So the average velocity was greater over the first 2 hours than the last 2 hours. All right, an example. A truck enters the off-ramp of a highway at t equals 0. Its position after t seconds is this equation from 0 to t to 5. So we want to know how fast the truck is going at the moment it enters the off-ramp, and then we want to figure out if the truck is speeding up or slowing down. So the truck's velocity at time t, we take the derivative of the position function, and we get 25 minus 0.9 t squared. And then the truck enters the off-ramp with velocity at 0, so it's 25 meters per second. And since the velocity is decreasing, the truck is slowing down. All right, motion under the influence of gravity. Thanks to Galileo, we have the following formulas for objects tossed in the air near the Earth's surface. We have a position or height of s of 0 plus v sub 0 t minus 1/2 gt squared. And then we have the velocity is the derivative of the height function. And the constants s sub 0 and v sub 0 are the initial values. S sub 0 is your initial time. Your initial position. V sub 0 is your initial velocity, and g is the acceleration due to gravity on the surface of the Earth, where g equals 9.8 meters per second or 32 feet per second squared, depending on which units your problem is asking you for, decides which g you will use. So we can find the object's maximum height by using velocity. If velocity is positive, then the object is rising or it's going up. And when the object's velocity is negative, it's going down. So if you have a velocity that's going from positive to negative, somewhere in between there was the object's maximum height. And at that moment, the velocity is 0 or has a horizontal tangent line. So the maximum height is attained when the velocity equals 0. So example, a stone is shot with a slingshot vertically upward with an initial velocity of 50 meters per second from an initial height of 10 meters. So here's your initial height, or s of t, and here's your initial velocity, v sub 0, s sub 0. We're going to find the velocity at t equals 2 and at t equals 7, and we're going to explain the change in sign, and then we're going to figure out what is the stone's maximum height and when does it reach that height. So we have s sub 0 equals 10, v sub 0 equals 50, and g equals 9.8. So if I plug that into my position or height formula, I will get 10 plus 50t minus 1/2 9.8t squared, and my velocity will be 50 minus 9.8t. So when I plug in 2, my velocity is 30.48 meters per second, and when I plug in 7, my velocity is negative 18.6. So it's rising here and it's falling here. So it's positive here and negative here. All right, the maximum height is attained when the velocity is 0. So we have to set the velocity function equal to 0. And when we solve that, we get t equals approximately 5.1. So the stone reaches the maximum height when t is 5.1 seconds. So now we plug 5.1 into our height formula to get 137.6 meters. All right, one last example. What initial velocity is required for a bullet fired vertically from the ground level to reach a maximum height of 2 kilometers? Well, we need a formula for maximum height as a function of initial velocity. So we take v of t and we get v sub 0 over g. So the maximum height is the value when t equals v sub 0 over t. So we'll plug v sub 0 over g in for t into our equation and get v sub 0 squared over 2g. So now we can solve for v sub 0 using the value 9.8 meters per second. So we plug in 9.8 meters per second here, and we get v sub 0 squared over 2 times 9.8 equals 200 meters, because that is our height that we're looking for. When we solve that, we get that it equals